This is 6.2.3.1. We're going to relate the discrete time Fourier transform and the discrete time Fourier series for the same periodic sequence. We have told you in the past that for periodic sequence, typically we use DTFS, but we also said that we can use DTFT, and today we'll see why using the same periodic sequence xn. Xn repeats every n samples. In this example, it is clearly that n equals to 6. The DTFS equation says that to find the frequency representation of this nth periodic sequence, we take the sequence xn, take the single period, and then from n equals to 0 to 5 for these samples, we multiply by this complex exponential with fundamental frequency 2 pi divided by 6, where this 6 is the capital N. We take this complex exponential with this fundamental period 6, and then allowing different harmonics from k equals to 0 to n minus 1. In this example, is k equals to 0 to 5. We then calculate the DTFS coefficients. So that's the basic idea of DTFS. Now, the typical DTFT equation is this. And when you try to use this equation to calculate the DTFT on the periodic sequence, you realize that you have no chance, simply because n equals to minus infinity to infinity exists for this periodic sequence. So this sum will not converge for any omega, apparently. There's another way to calculate the DTFT, and that is the trick of using the delta function. When we use the delta function for the analysis, and then we'll use a delta function again for the synthesis, you'll realize that it does work. Let us see how we will express the DTFT of the periodic sequence using this formula over here. So simply, this is a trick. The trick is that we would compute CKs as in the DTFS and plug into this representation for DTFT. So we do not compute DTFT directly from this equation. We compute the DTFS, plug in the CKs, multiply it by 2 pi, multiply it by the delta for different frequencies. And these different frequencies are exactly at 2 pi nk, which is here, 2 pi n over k. So this is the trick that we have used, because in the past we have told you that x of omega is a continuous function. But the Fourier series told us that when the signal is periodic, we only need to use the harmonics at 2 pi over n times k. Now, to prove why x omega, the DTFT representation of the periodic function, works, let us now take x omega and plug it into the DTFT synthesis equation. This is the DTFT synthesis equation. It says that xn is 1 over 2 pi integrating from minus pi to pi the DTFT representation ej omega n. And we are going to plug in this x of omega given by the previous slide, where it is a weighted CKs times 2 pi at this delta at this frequency. Let's plug it in. Now, the basic idea is that once we have plugged in x omega into this equation, we can interchange the integration and the summation. We will not prove why this is possible. This is beyond the scope of this book or this course, but let's assume that we can perform this substitution, and we will now be able to cancel the 2 pi's. We would now bring the integration into the expression, and we'll realize that the integration is operating on omega, and it will be on the particular frequencies 2 pi over nk. Using the shifting property of the delta function, that means this delta function exists only at this particular frequency multiplied by ej omega n. Therefore, this omega and this omega are the same, and what it implies is that we would be only extracting ej omega n at this particular frequency, reducing the DTFT into the DTFS synthesis equation over here. And then, since we believe that the DTFS synthesis equation will reconstruct x of n, what it means is that both the DTFT synthesis and the DTFS synthesis equation will result in the same xn. So to conclude, the DTFT and the DTFS represents xn slightly differently. The DTFS generates the CKs, while the DTFC requiring not only the CK but the delta function at the particular frequencies. In the next slide, we'll give you more examples. Thank you.